Biminimal structure spaces. They have been presented in 2010 by Boonpok from Thailand, and in general several authors from this country contributed to this study of these spaces, and until today, as we can read here, there are several papers devoted to this topic. For example, there are papers about density, continuity, separation actions, and the notion of exterior in biminimal spaces. And neutral structures of this type are being studied too. If you are interested, here you have some kind of bibliography. Okay. We know that a subfamily of the power set of some non-empty universe X, subfamily Mx, is called a minimal structure on X, if and only if the empty set belongs to this subfamily and the whole universe belongs to this subfamily. So these conditions are rather very general and weak. Now assume that there are two minimal structures on X, say M1X and M2, and then this triple X, M1, M2 is called a biminimal structure space. Clearly this is an analogy with bitopological spaces. For example, finite universe A, B, C, D. The first minimal structure is this one, okay, empty set, the whole universe, and moreover we have singleton of A and this subset which contains A and B. And we have the second structure, here we have A, B, C, D, and of course the whole triple is a biminimal structure space. Or we have this set of real numbers, and the first minimal structure contains, of course, empty set, the whole universe, so the whole real line, and let's say all open intervals of the form AB. Why not? 3, 4, 0, 1, minus 1, 1, and so on. And assume that the second structure contains empty set, real line, and all singletons. Okay, no problem. Of course, any topology, any generalized topology, any infratopology is a minimal structure too. Now, we say, and all those definitions are taken from the initial paper by Boonpok and from other papers on this topic, they are not our own. We say that a subset A of biminimal structure space is called M1, M2 closed if the closure with respect to the first of those minimal structures of the closure with respect to the second of them is A. Sometimes we may use the notion of MIMJ closed. This will be later. And as for the complement of such set, it's called open, M1, M2 open. This is clear. One can prove if we have two M1, M2 closed sets, then their intersection is closed too, but their union may not be M1, M2 closed. For example, very simple counterexample, X contains 3 elements, 1, 2, 3, let's say. We have these two minimal structures, so the whole construction is a biminimal structure, and one can check that singleton of 1 and singleton of 2 are M1, M2 closed. If singleton of 1 is closed in this minimal structure as a complement of 2, 3, and so it's closed, and so its closure is just itself, and then it's closed in this structure too, again as a complement of 2, 3. Similar reasoning may be applied to singleton of 2, but on the other hand, their union, 1 plus 2, is not closed, M1, M2 closed, because its closure in both minimal structures is just X. So it's different than this set, than 1, 2. The authors formulate the following theorem. If we have two minimal structures closed under unions, then the set A, some set A is M1, M2 closed, if and only if it's both M1 and M2 closed. Moreover, one can prove that if that A is, without this assumption about closure under unions, that A is M1, M2 open if A is just like interior, the first interior of the second interior of A. Okay, if two sets are M1, M2 open, then their union is M1, M2 open, but their intersection may not be M1, M2 open. As I said, there are several topological notions in the structures. They've been studied already. Among them, there is density. There's a paper about density, and we say that A is MIX, MJX. It should be dense if it's MI closure of MJ closure of A is the whole universe, where IJ are 1, 2, and I is different than J. I is different than J, but it doesn't mean that those minimal structures are necessarily different. It is possible that we have M1 just like M2. In fact, it collapses to singular minimal structure then. And here we have an example. You may check this. Very simple space, 1, 2, 3. Those two minimal structures, perhaps they've been already used. And moreover, we've already discussed this set 1, 2, and we said that its closure in both spaces is X. And now we can see that M1, M2 closure of this set is indeed X, and moreover M2, M1 closure is X2. So from both perspectives, M1, M2 and M2, M1, this set 1, 2 is dense in the space. And there are several theorems. For example, we may prove that if A is MY/MJ dense, then for any non-empty MI/MJ closed subset F, such that A is contained in F, F must be equal to X. And if A is dense, then it's here non-empty intersection with any non-empty MI/MJ open subset. And moreover, here is a mistake. It should be X minus A here, of course. So this is the notion of exterior, MI interior of MJ interior of X minus A, it should be, is empty if and only if A is MI/MJ dense. And here is again our bibliography. If you are interested, you may check exterior set in neutrosophic biminimal structures, and the whole perhaps doctoral thesis, a study of generalized closed sets in minimal and biminimal structures. And there are some other papers too. Thank you very much for your attention.